Hi, I'm Kathleen Lang, a student in the Data Science Master's program at Regis University. This presentation will detail my Practicum 1 project, which is entitled Astronomical Object Classification of Simulated Large Synoptic Survey Telescope Data Using a Neural Network. Throughout this presentation, I'll discuss the project description and motivation for why I chose it, and then I'll go through all of the data science tasks that I completed, and then I'll complete it with looking at some future work and how I could have made improvements. The data for this project comes from simulated data that will mirror data coming from the LSST telescope, which is currently being built in the Atacama Desert in Chile and will be fully operational in the year 2022. The size of the primary mirror and the camera for this telescope allows it to have a 3.5-degree field of view, and just for reference, as seen on the image on the right, this field of view is equivalent to about 7 full moons. The telescope will be able to detect light-varying astronomical objects such as Cepheid stars or supernovae or eclipsing binaries, among others. And as the telescope scans across the sky, it will use different filters in front of the camera to be able to capture different wavelengths or passbands of light. Because the field of view is so large, the telescope will be able to map the entire southern sky every 4 nights with very high resolving power. So this results in about 20 to 40 terabytes of data every single night. And along with the large amount of data, there are also difficulties with regard to its cleanliness. Some of these issues include the image quality due to particulates or clouds in the sky or too much ambient light coming from the moon's current phase. Another problem is due to the fact that a lot of the redshift values are unknown, which is a standard method of normalizing this type of data. And also periods of the time variance can be really irregular depending on the type of astronomical object or with respect to the planned intervals for when the telescope is pointed at a particular object. So with all of these data challenges, the telescope scientists reached out to the Kaggle community to get help in creating a classification algorithm that'll be able to sort the data as quickly as possible and then filter out all the useful versus non-useful information. I chose this project because it coincided with my astrophysics background while involving many of the steps in the data science project life cycle. I particularly chose the neural network algorithm as my classifier because during my coursework here, I haven't really had an opportunity to implement one and wanted to try my hand at it before graduating and entering the workforce. The methodology for the project is to first download the data from the website. Very little pre-processing was necessary because the data set organizers already had basically cleaned it up. I used Python and Jupyter notebooks to code everything, and those notebooks are available on my GitHub page. I started the project doing some exploratory data analysis of both individual light curves and the metadata. The following slides will detail just a few of the most informative plots that I found. Here we see an example light curve for a single object. The x-axis is the date that the observation took place in modified Julian date, where each increment represents 1 day. Due to the planned timeline for how the telescope scans across the sky, the straight lines or the flat lines in the middle portions correspond to the times that the telescope is actually looking away from that object, and the bumpy parts or the noisy regions are when the telescope has the object within its field of view. The y-axis represents the light flux received from the object. This is a measurement of the brightness of the source, and intuitively this flux should always be a positive number because it's a summation of the light received. However, the flux is calculated based on a reference image for that portion of the sky, so sometimes it can go negative if it is lower than the reference image. Each of the different bands represents a passband or wavelength that are distinguished by different filters that are placed in front of the telescope. U represents the ultraviolet range, and it goes all the way down to the I, Z, and Y passbands, which are all ranges in the near IR. Each object and its light curve are labeled with a target value. These target values are random integers that represent a single astronomical source. For example, target 42 could represent a type 1 supernova. The data creators decided to do it this way to reduce any domain knowledge bias for the competition. I continued by looking through different types of light curves to try to understand how they compare to each other. On this slide, we see two different examples of light curves. The top one is target 92, and it shows a light time variance that has a large amplitude and a period that's fairly short, on the order of a couple days or less. Target 6 below shows a more Gaussian-like light curve where there's a steady increase in flux and a steady decrease. This also seems to be like a one-time event because flux before and after the peak are near zero. After looking through the training flux data, I moved on to look at the metadata for all of the objects. The first graph I produced shows the distribution of objects per target. Target 90 is by far the most common object type with over 2,000 instances in the training set. The least common target with less than 100 instances is target 53. Also, this graph shows whether the targets are located within the Milky Way, which are orange labeled, or if the object is extragalactic, which are blue bars. The interesting thing this graph shows is that there's no overlap of object type and whether they are located inside or outside of our galaxy. Therefore, it will probably be very useful to use this origin as a feature for classification purposes. Next, I looked at the lateral distribution of objects throughout the sky. The first graph in blue shows the positions in Earth coordinates, while the second graph shows positions in galactic coordinates. Each different target is displayed as a separate color. And from both of these plots, it's easy to see that there's no major grouping of one type of target in a specific location, and they're all fairly evenly distributed laterally throughout the sky. Therefore, using the location metadata will not be useful in classifying these objects, and I'm going to remove those columns from the final feature set. The next step in my process was to do feature engineering to create descriptive variables that could be fed to the machine learning classifier. Since there were two different datasets, I needed some way to combine them. The first approach was to create manual features based on aggregations of the flux data. I grouped the data by object ID and then calculated standard descriptive statistics such as maximum, minimum, mean, etc. I also added in some calculated features such as the flux weight, which is the flux value normalized by its measurement error. Next, I merged the flux and the metadata data frames, where each new aggregation or calculated value became a new column. The second method I chose to use was using the feature tools package in Python. And to use this, you create an object called an entity set, which contains each data frame and then defines the relationship between the two of them. You next tell the feature generation method what type of aggregations you want, like sum or standard deviation, and then you tell it how you would like the columns to be transformed or combined, such as multiplying them or taking the difference. The max depth parameter states how many different columns should be combined for a single feature. This is a really helpful package because you can have it auto-create features for you without telling it the parameters for aggregation and transformations. Finally, once all the features are created, is it really important to standardize the features so that when they're fed to the neural network, one isn't drastically larger than the other and then automatically overweighs or overpowers another feature. After creating the features, the next step is selecting the most important ones to use for training. One method is to just use all of the features created and let the neural network sort everything out. Deep learning networks are actually much better at sorting out important versus not important features than other machine learning algorithms, but you still have to take in consideration that as the number of features increases, so does the training time. So I created a couple of datasets that kept all of the features, and then I created a couple of datasets that had a reduced number of features. I explored three different methods of dimensionality reduction. The first was mutual information. For this method, it measures how much knowing one of the variables reduces the uncertainty about the other, basically the dependence between the two. Next, I used feature importances based on random forest classifiers. The idea here is that features at the top of the tree or that have a higher rank factor more into the final predictive power than lower ranked features would. The last technique I explored was looking at a heat map of the correlation matrix to remove highly correlated variables. Combining these three different methods of feature reduction and taking into consideration important features that I determined during the EDA process, I came up with a list of 18 of the most important features, and after standardizing them, used these as training sets for the neural network. The biggest portion of this project was spent building and optimizing the neural network. I started with the Python library Keras, and in this library, you define the model as sequential, and this allows you to build up the network a single layer at a time, starting with the input layer and then followed by X number of hidden layers and ending with an output layer. The next step is to define the number of nodes in each layer. This value is really important because too few nodes can lead to underfitting of your model, but too many can lead to overfitting and also really increase your training times. One rule of thumb that I found in a number of different articles, including this Heaton research article, was to use the equation 2/3 times the number of feature plus the number of classes. Next, define the input layer. The standard layer type is dense, which means that every node is connected to every node in the subsequent layer. The standard nonlinear activation function for hidden layers is ReLU, which is 0 for values less than 0 and a sloped line for values greater than 0. And the input shape will match the number of features. We continue by adding hidden layers one by one. Another rule of thumb says start with one hidden layer to understand initial performance of the model, and then adding hidden layers allows the learning algorithm to start exhibiting nonlinear behavior. A couple of methods to reduce overfitting and reduce the training time are to use batch normalization and a dropout rate. Batch normalization standardizes values after every step to make sure that you're preventing activation functions from creating values that go really, really high or really, really low. Dropout randomly shuts off a certain percentage of the nodes from each layer during a training stage because sometimes nodes that are close together can become codependent, and this isn't what you want in your neural network. The output layer has the number of nodes equal to the number of classes to be predicted. Because this is a multi-class classification model, then the activation function on this layer becomes softmax. Finally, we compile the model using the standard optimizer of Atom, which is related to the learning rate, and the loss function of categorical cross-entropy, which is the metric trying to be minimized. Next, I trained the model. To understand the performance of the algorithm, I did a couple different things. First, I plotted the model accuracy for every epoch of the training cycle. One way to spot overfitting from these graphs is when the training curve, which is in blue, is far better than the testing curve, shown in orange. So although the plot on the left has a lower accuracy, it is not overfitting at all compared to the plot on the right, so the model is probably better for the plot on the left. I tried to also optimize the model in a number of different ways by changing the activation function, the optimizing function, and altering the number of epochs and batches, among other things. After this first few rounds of optimization, I found that the manually created feature set from just the aggregate values consistently outperformed the others, and so I continued to work with only this data set. The next method I used to evaluate the model was to use k-fold cross-validation. This splits the data into n groups and then trains on n-1 groups. Once all the groups have been iterated over, the individual metrics can be combined to get a more accurate description of the model's performance. Using 5 folds, the accuracy of my model was almost 78% with a standard deviation of 1.33%. I used the confusion matrix to see how accurate the model was for predicting individual targets. For targets 88 and 65, the model did a pretty good job with predicting them as 96% accurate. Targets 62 and 42 had much worse accuracies and were only correct about a third of the time, and the model did a terrible job at predicting target 52 by classifying it as target 42 every single time. I finally ran the model in the test set of data, which took about 3 hours to complete because the file size was almost 20 gigabytes. And as shown in these two above charts, unfortunately my model did actually a pretty terrible job of predicting actual targets, even though my validation testing was 78% accurate. Out of the 14 different targets available, my model only predicted 5 of them, and those weren't even always the correct predictions. With only 8 weeks to complete the project, I didn't have a lot of opportunity to improve on my final results. But to get better results, I'd start by improving the features I generated, such as fitting the curves with the Gaussian function or looking at the ratios between the different passbands. Then I'd look at how the training set compared to the test set data. I assumed that the training set was just a sample of the testing set, but this actually turned out to be a little misleading as I was looking through some discussion posts on the challenge forum. Finally, I like to see if breaking up the data set into subsets like extragalactic versus galactic objects would improve the final performance. This project turned out to be really challenging, but I learned a lot along the way, and though my final results were far worse than I desired, I've become a lot more confident in my data science skills. Thanks for listening, everyone.